Hello everyone, welcome back to Introduction to Semiconductor Devices. Uh, we are starting the third week of the course. So in the last lecture, we were talking about the impact of temperature on Fermi energy, and we have introduced the concept of carrier drift. How do the electrons move when there's an applied electric field, or how do the holes move? We introduced the concept of drift current, which is given by this expression here. Essentially, the drift current is proportional to the electric field, and then you have a coefficient of proportionality mobility in the expression, and then the concentration and the charge. And then we went on to talk a little bit about mobility and resistivity, which are important parameters in a semiconductor. And we showed how, by introducing dopants, we are able to reduce the resistivity. Okay? So for N-type and P-type carriers, we have showed how this thing happens. And then we have also estimated, we asked you to estimate how the resistivity can be calculated. And then we went on to talk about compensated semiconductors, which are essentially semiconductors where you have both electrons and holes present, or rather acceptor and donor dopants present. So we have to take the net difference, and that we can derive by actually what is known as charge neutrality relationship. We showed you an expression for this, and then we derived the carrier concentration for electrons, and we said that that could be applied for holes as well, by a small modification. And towards the end of the lecture, we were talking about what happens to the carriers, the physical picture, or sort of the band diagram picture, right? Or the physical picture, what happens, when you apply an electric field. And we said that if you have electric field applied, let's say positive terminal to the left side and the negative terminal to the right side, as shown here, there will be an electric field in this positive x direction. If you call this as x, the electric field is in the positive x direction. So now, because of that, the holes in the semiconductor would move in the positive x direction, and electrons would move in the opposite direction. Right? This is what happens when you apply electric field to the carriers. So what is the magnitude of the electric field? Well, it will simply be the distance, the length of the semiconductor. Let's say this is L. So electric field will be simply the voltage applied by the length, right? Voltage per centimeter in our case. Okay, so what happens? We showed that the electrons acquire a kinetic energy, okay, as they travel across the semiconductor. Even the holes acquire the kinetic energy as they travel across the semiconductor. And we wanted to represent it in form of a band diagram. And to do that, we have argued based on the photo excitation. Let's say if you have a band like this, EC and EV shown here, and have an electron at the edge of the valence band. It's basically bonded to the silicon atoms. Okay, so you have an electron there. There are lots of electrons in the valence band. Now, if you shine a photon of energy Eg, like if this is my band gap Eg, if I shine a photon of Eg energy, then the electron will essentially be, the bonds will be broken. Electron will move into the conduction band. Okay, exactly into the conduction band. But it doesn't have any more energy. All the energy has been consumed for breaking the bonds. So it doesn't have any more energy. So it will be at the EC. Okay. Now, if you use another photon with a higher energy greater than Eg, like if I use h nu, I'll put it in blue. Let's say h nu greater than Eg. Okay. Then the electron from the edge of the band would be excited to the conduction band, but it would actually acquire additional energy. Okay. So this additional energy is essentially h nu minus Eg. So when the Eg amount of energy is consumed to break the bond, and the additional energy is transferred as kinetic energy. So electron starts moving. So whenever an electron moves in a band, we show that the kinetic energy is essentially proportional to the distance from the EC. So that's why we are writing here that as you go away from the EC, the kinetic energy of electrons increases. Okay, and similarly, you could talk of holes. The same picture actually. I mean, you just have to reverse the arguments. You take an electron from deep within the valence band and then excite it up to the conduction band edge. You could repeat the same arguments, and you will see that the kinetic energy of holes essentially becomes proportional to the distance from the conduction band, a valence band edge in this case. So in this case, if you have a higher energy hole, it will be something like this. So it will be deeper in. Okay. So this is what we introduced. Okay. Now, we would like to understand how do we represent that in a band diagram. Okay. So now let's, just for sake of continuity, I had put this diagram again. So let's say we have holes going in this direction and then electrons going in this direction. Okay, this I'll call it as x equal to 0, and this I'll call it as x equal to L. Okay, the distance, the total length is L. So now I'm interested in drawing the bands. How do I represent? We understand that as electron, let's say electron initially was at rest at x equal to L. Okay, let's assume electron is at rest at x equal to L. Okay, so and then as it moves towards x equal to 0, it's acquiring kinetic energy. To show that, what I can do is I'll represent the bands in this fashion. Okay, so I'll say EC, EV. So if this was my x equal to L, let me, this is equal to x equal to L, and this is going to be x equal to 0. As it travels, so initially my electron was at rest, so it will be somewhere here. As it travels, it gains kinetic energy that can easily be represented by this line. It just acquires energy. So by the time it comes to the left edge, electron might be somewhere here. So this is the amount of kinetic energy. Sorry, this is Ki of electron. Okay. A similar analysis works even for holes. Holes move in the positive x direction. So let's say initially the hole was, let's say there is a hole here which is at rest. So it's at EV, and as it travels in the positive x direction, it acquires kinetic energy. So eventually it might end up somewhere here. So this we will show as kinetic energy of holes. Okay. So what are we doing here? So the electric field in a semiconductor is essentially being represented by the gradient in the bands. Okay. So let me see. What this kinetic energy is essentially going to be proportional to the electric field, isn't it? So greater the electric field, greater the velocity, and greater the kinetic energy, right? So how is it related? To do that, we could essentially write out, we know that Q times electric field, the charge times electric field is essentially the force, and force times the distance is the energy, right? So you could easily verify this, that electric field is going to be 1 over, let me call it E, okay, charge of electron times dEc by dx. Okay. You could easily verify this, E times capital E, electric field times charge is going to be the force, times the distance is going to be the work energy, right? So, well, you could also, you don't have to write it only as EC, we can also write it as 1 over E dE V by dx. Or you could also use it in terms of the intrinsic energy, 1 over E dE I by dx, any of them. Yeah? Okay. So essentially your intrinsic energy level is going to be in the between. Right. So what we are saying is the electric field applied is going to be represented with the slope of the bands. Okay. Now let's say you are new. Okay, you're drawing band, because band diagrams are very, very helpful in understanding the physics of the semiconductor device. Okay, so you're new and you're confused. At some point we asked you to draw a band diagram, and you draw something like this: EC and EV. Would it be I'll say that there's an applied electric field here, which is like this. So if I draw bands like this, would it be correct? So is this band diagram correct? Think a moment. Okay, I'll say is band diagram correct? Okay. If you think it is correct, why it is correct? If you think it is wrong, why is it wrong? Okay. You can pause the video a moment and then think about it. It turns out that this is incorrect. The reason for that is we are essentially saying that as the field is applied, You remember always EC minus EV is going to be your band gap. This is EG, right? And you're showing that the band gap is increasing. So this implies, if this was correct, implies EG is increasing with X, right? And that is not possible. We saw, if you think about the physical origin of the band gap, we saw that it is because of the lattice structure, and then you have the energy levels interacting, forming bands, and so on. Just by applying electric field, I'm not going to change it. The only way to change that would be to modify the lattice spacing. Okay? That we are anyway not doing. Just by applying an electric field, we are not really going to modify the lattice spacing. Okay? So EG is not going to change, and because of that, your band diagram like this is wrong. Okay? And even from the energy arguments, you could say that, because as the electron is traveling here, if I apply this sort of this thing, kinetic energy of electron is like this increasing, whereas what happens to hole? The kinetic energy is actually not increasing, right? So that is again a wrong argument. So essentially this sort of a picture, if you come across, this is one way to verify your one way of sanity checking. Okay, so always the EC and EV are going to be parallel unless we introduce what are known as heterojunctions, and that is another story. Okay? For a simple, if you take a simple piece of silicon, it is going to be always parallel to each other. EG is going to be fixed. If you use silicon plus gallium arsenide, something, different material, silicon germanium, something, I add a different material, then I could modify the bands a little bit. Okay? Anyway, all right. So this is how a semiconductor behaves in an electric field. Let's try a simple problem. Okay. Well, this is a hypothetical band diagram that you're seeing on the screen, and always remember that on the y-axis, whenever we are talking of energy band diagrams, right? On the y-axis here, this essentially means energy of electrons is increasing as you go higher on the band diagram, and conversely, if you go lower, energy of holes increases. Remember, we said as the hole was deeper into the valence band, it has a higher kinetic energy. So basically, energy of the holes increases as you go lower, energy of the electrons increases as you go higher. So you have a band diagram like this. The first question we'll ask you, let's try to analyze. I mean, this is a hypothetical scenario. It's never going to be realistically there, but let's analyze. Let's say at x equal to 0, this be x. So what is the electric field across this semiconductor, some semiconductor, and you have the bands. One important feature that you should note here is the Fermi level. This is Fermi level here. This is EF, right? And EF is shown to be constant in a semiconductor. That is, under equilibrium, whenever you have equilibrium conditions, EF is constant. It cannot change with X. Okay, there is no gradient in EF. The reason for that is, suppose it is not true. What happens? When EF is not uniform, then electrons from the higher energy, higher EF regions can travel into the lower EF regions and then equilibrate. It's sort of like, if you have a tank of water, the top of the water, if you take the EF as, the level at which the water is there, at the top of the water level is there, that is never going to be different in a particular tank, right? It's always going to equilibrate. So if by chance you start pouring water from one side of the tank, even then it will simply equilibrate, and then you'll sort of have a constant uniform level of water, right? Similarly, in a semiconductor, I mean, we'll again go back and explain it a little bit more later on. But essentially, under equilibrium always, you see that the Fermi energy is going to be constant. So, okay, fine. Now, what is the electric field across this structure? How do we analyze that? We said that electric field always is going to be electric field 1 over Q dE C by dx. Well, sometimes I'm using E and sometimes Q, I mean, charge of electron, because when I write E, it can be confusing with electric field when I talk about it. So Q might be better in some occasions. So you understand that anyway. Electric field is equal to gradient of the conduction band. So if I want to draw the bands, electric field, so it's going to be this way. This is going to be my X, and this is going to be my E, right? So at x equal to 0 and x equal to L by 4, you have certain, negative slope. So the field is going to be negative, and it's a constant slope. So it's going to be a constant number. And then from L by 4 to 3L by 2, there is like no gradient. So it is going to be 0. There is no field. And then this is L by 4, and till up to 3L by 4, there is no gradient. And then again, there is a negative gradient. So it is going to be this way. Okay. So this will be L. Okay. So this is how your electric field is going to be in a semiconductor. Remember always, because we will be showing you band diagrams of PN junctions, MOSFETs, MOSFETs. Always, whenever you see, if you see a gradient, along the gradient, holes will travel, electrons will travel opposite to the gradient. Okay. This is how you should think about it. All right. So this is your electric field. How about the kinetic energy of the electrons? What happens as they travel? So to analyze that, let us draw it one more time. So axis, I want it in black axis. Okay. So along X, along your kinetic energy on the y-axis. So let's start from L equal to 0. Let's say that the electron, this picture, the red dot here is representing an electron. So electron has 0 kinetic energy at x equal to 0. So I'll put a 0 kinetic energy here. And then as it travels, it acquires a certain kinetic energy, right? Because how is electron going to go? Because electric field is negative. That means DEC by dx, right? So this is like this. Electric field is pointing in this direction. Electric field always points in the gradient, in the positive gradient in the EC, right? So if the electric field is pointing like this, holes are going to move like this. Let me say P is going to move in this direction. Electron is going to move in the opposite direction, right? So electron will acquire energy, and that can be displayed by this. And then of course there is, if I sort of move this electron across the middle region, it's not, the bands are constant, there's no extra electric field there. So you'll see that the kinetic energy is, it's going to remain constant here. It's not going to change. But then when you reach the 3L by 4, it's going to be 3L by 4, then this is going to be L by 4. As you reach 3L by 4, you have again a field there, which is going to cause it to accelerate, and then you're going to have a higher amount of kinetic energy. So this is how kinetic energy changes. Okay. It is possible to actually avoid some of these things, but when we talk of barriers, potential barrier in a PN junction, it will be useful to revisit these concepts. Okay. So essentially what we are trying to do is build up a toolbox. So by the end of this week, our toolbox will be done. So we'll have all the basic tools necessary to understand semiconductor devices. And then next week onwards, we'll talk of PN junctions and so on. So when we talk of these potential barriers and all that, these concepts will be useful. That's why I'm just covering it right away, so that you have some time to review. And then when we talk about devices, we can understand it easily. Okay. So this is how kinetic energy changes. Well, we also have something called as potential energy, right? Kinetic energy and potential energy. In this case, essentially, we are not taking any other external effects into account. So whatever potential energy change is going to happen, that is going to happen only because of the electric field, in which the carriers are changing. So we know that potential energy can be defined as basically with respect to a reference level. So in this case, what we do is we define the potential energy of a carrier, let's say electron. We're going to define as PE is going to be EC minus a reference. Why reference level is a constant level. It could be, typically, in our case, we can take it as typically EF. EF is an easy reference for us. Okay. Because EF is going to be constant everywhere across the device in equilibrium, so you can take it. And why EC? Well, we are saying that the potential energy is simply going to correspond to the changes in EC. So whenever you apply electric field, the bands are going to bend, and that is also going to be a measure of your potential energy, because no other forces are involved. Okay. So with this, we could draw the potential energy also, same as similar to whatever we have done in the case here. So here it's going to be x. Sorry, I should keep it as x. This is going to be a potential energy. So initially, let's say there is some potential energy x at x equal to 0, right? At this point, let's say P is equal to some number. I don't know. Let's just call it E naught. Okay. So we started out with E naught here because essentially at that point your kinetic energy is 0. So whatever energy is E naught is going to be a potential energy, and as it traverses, what is happening? Essentially, your this is your potential energy definition. Basically, the distance from the EF. So as you're traveling, the bands are bending, because of which your potential energy is going to reduce. So it's going to reduce. So my hand is all right. It's going to reduce, and then the bands are constant. So it's going to be like this. Again, it's going to reduce further. Okay. So essentially, this is L by 4, and this is 3L by 4. So what you see is in band diagrams, the potential energy is going to of electrons, potential energy of electrons follows EC profile. So whatever the shape of EC, that similarly follows for electrons. And once you have potential energy, you can define potential. Simply is going to be Q times the potential. Charge times the potential is going to be potential energy. You can think about it. We will revisit this later. Okay. All right. So this is how this is about how semiconductors behave in an electric field.